The next application to our vector problems, we're going to look at some navigation problems again. And a lot of times you'll see these as either looking at boats on a river where there's a current acting upon the boat as well as the propeller, or there's also navigation with planes and then the wind acting on the planes and the other forces there too. So here's a quick little demonstration of a boat in the current problem. We'll talk about a plane one in this video, but here's just kind of what's going on there too. So here's a little applet. You can see there's two vectors here. The boat here, the red vector represents the current. You can see it kind of scrolling across the screen there in the direction, whether it's working into our boat, it could be working against our boat or across our boat. But the current here, let's pretend that it's maybe going in this direction here with that magnitude. So it's got a magnitude of 5.5, 57.4 degree angle. Now what we want to do here is figure out what vector would produce. So this is the boat velocity vector. All right, so right now if we point our boat kind of in that direction, okay, for a boat in a current, the resultant of those two vectors should be the path that our boat's going to take. The current is pushing the boat kind of back up into that direction. Our boat is going to propel itself into that direction. And if you think about the resultant here, where are we going to be heading? Are we going to hit that island or not? I don't think so. So what we want to look at doing is we got to kind of drive into that current a little bit. And then that might be close. The resultant there, if we put these right on the back of the boat here, maybe even on the front of the boat, we can see that the resultant of those two vectors will take us in a path kind of towards that one. It looks like we need to go just a little bit further. And let's try that one. Let's see if we hit the island here. Start. So you can see the current's pushing. And you betcha the resultant of the boat speed and current speed is then the actual track the boat will take. All right, so that's the idea there. When we're working with other applications, the big one is planes. There's a couple of vectors involved with planes here that we need to be concerned with. So we'll go ahead and set these up and talk about each one of these vectors. The first vector associated with planes is something called the airspeed. That's just going to be the speed of that plane relative to the air. It's not the speed relative to the ground like we would consider as 5 miles per hour. On the ground you would cover 5 miles in 1 hour. This is the speed relative to the air itself. So up in the air, how fast is that plane going? Kind of, if you don't quite understand what that means, it's not a real big deal. The other vector that's going to act on the plane is actually the wind. The wind will force these planes off course, and depending on the magnitude of the wind and the direction of the wind, that can affect the path that the plane needs to fly to get to its destination. If it's behind you, it's actually going to speed up your flight. If it's into you, it's going to slow you down, and you have to apply more force from the jets. But those two kind of produce the other one, and that's something called ground speed. The ground speed is relative to the ground. So if you're going from, San Francisco to New York, okay, how many miles is that? How long did it take you? That's going to be your ground speed. Okay, how much ground did you cover per hour? Now this ground speed vector is always going to be represented by the vector sum, or the resultant, of airspeed and wind speed. Okay, so those three vectors are all the forces that we're going to be concerned with when we're dealing with airplanes, flying a plane throughout the air. We looked at the boat problems. You get the current vector, you get the propeller or the boat vector, and then the resultant of those two is the path of the boat. So let's take a look at an example here and see if we can't solve one out. With these ones, like before, the navigation problems, the sketching is a big important piece of it. So we got to make sure we have semi-detailed sketch, and we will incorporate that bearing idea. So a plane with airspeed of 192 miles per hour is headed on a bearing of 121 degrees. And remember, if there's just the one measurement given, that's always from due north, and due north on paper is straight up. So we're going to start here. We're just going to draw in a due north line. Okay, so we'll just draw in, that's an arbitrary line. It is not a vector, but here's what we would call due north. Okay, all right, so this plane has an airspeed of 192 miles per hour. All right, so we could draw that. It's on a bearing of 121 degrees, and again, these sketches don't have to be perfect, but it is nice if we use some kind of compass here to sketch those angles. So I got one here, 121 degrees is approximately right there. Oop, just slipped off it there. Let me slide it over. Okay, so there's 121 degrees. I'll produce that vector. Now again, that's from due north. Okay, so our due north line, we want to put one edge of that angle on the due north line, and the other one is where our plane would be sitting. So we'd kind of assume that our plane is right here at the moment. All right, and then again, that angle there is 121 degrees. All right, so that's the airspeed. It also says a north wind is blowing from north to south. So a northern wind blows from the north to the south. An eastern wind blows from the east to the west and this one's going at 15.9 miles per hour. So if we draw on a vector, this one will just kind of sketch. Remember, it's coming from the north, a north wind from the north blowing to the south at 15 miles per hour. And we'll get these somewhat to scale here. I'm going to blow this one up a bit to go ahead and kind of get our scale out a little bit. So let's make that one a little longer. Remember, that one's 192 as a magnitude. And we might as well label that lower here, magnitude 192. And then this vector here, which is our wind vector, magnitude, we'll call it W, equals 15.9 miles per hour. So this one is the magnitude of airspeed. We'll call it magnitude of A. All right. Now, find the ground speed of the plane and the actual bearing of the plane. So here we go. Once we have the sketch kind of semi-drawn in, we can go ahead and go tail the tip. Remember, wind speed and airspeed, their resultant is ground speed. Okay, so the actual path of our plane, if our wind is blowing in that direction, we're trying to travel this direction, the actual path the plane is going to take would be the resultant of those two. All right. So again, the closer our sketch is to being accurate, kind of the better off we're going to be overall. But again, it doesn't have to be perfect in that regards. So we got a little sketch made up. Here's the resultant. This is going to be our G vector, or ground speed vector. That's the one we need to know the magnitude of, and we also need to know the magnitude of from due north, or excuse me, the bearing from due north to that ground speed vector, because that's going to be kind of the actual path of the plane. All right, so here we go. With these problems, it's never a bad idea just to kind of elongate a couple of these, because when we go tail the tip with the wind speed vector, we're going to produce some parallel lines. Okay. This one also being our wind speed vector down here, so the magnitude of 15.9. Okay. And again, our due north line and our wind speed vector in this particular case are parallel, which makes both of these, the airspeed vector and the ground speed vector, transversals. So what we'd be looking at is somehow, some way, we need to come up with a few angles here down in our triangle somewhere. So if we take a look at the 121 degree angle, and my sketch is a little small here. I'm going to see if I can't make this a little bigger. Let's extend the page a bit. We're going to group those together and drag them out. So our 121 degree angle, remember, goes to the blue line there. And we know that that one is 121. So this angle right here to the blue would be equivalent to this angle right here, because these are parallels, and this would be a transversal. So we would know now that angle, because of alternate interior angles, is also 121 degrees. All right. So with that, I think now we're looking at a triangle. It's not a right triangle, but we do have our law of sines and law of cosines. We know side and angle and a side, and these problems are generally different depending on what you know. You might have to use law of sines, you might have to use law of cosines, you might produce a right angle somewhere in there, so we got to be able to piece that together. But somehow, some way, we can come up with an angle in this problem and solve for the missing side. So this to me looks like side, angle, side. That's law of cosines. So the magnitude of G is going to be equal to 192 squared plus 15.9 squared minus 2 times 192 times 15.9 times the cosine of the angle between them, which is 121. Again, this, like I said, it's not always going to be the same angle that was given there. That just happened because of the due north or the northerly wind blowing to the south. All right, so if we simplify that out, we'll go ahead and give you a second there, plug that all in. We actually find that the ground speed vector is 200.65 miles per hour. Okay, so I'll pause this here. All right, so there you go. I went ahead and did the calculations on the calculator for us there. Just don't forget to take that square root in the end. And that is then the answer to part of our problem. The ground speed of this plane would be about 200.65 miles per hour. So, you can see that wind, even though it's not blowing from the back of the plane, it's actually helping produce a little faster ground speed than what the airspeed of the plane actually was. So it is helping us in a little bit of a way. Now, the other part of the question here says we want to find the ground speed of the plane and the actual bearing. So now we need to find the angle, the red angle there. Let's call it theta at this point. And we know it's 121 to the blue line. We just need to know what this little sliver is between the blue vector and our ground speed black vector. And if we can find that, we should be able to add that to 121, and that'll give us the actual bearing of our plane. So taking a look, to me, we know 15-point side, the side opposite it. So we're going to call this one right here alpha for the time being. So sine of alpha, that's what we want to find, over its side, 15.9, should be equal to the only one we can use right now. We know this angle is 121, and its opposite angle, our side length, is 200.65. So sine of 121 all over our 200.65. Careful, I'm not going to use that as a rounded value. I'll use the one up here on the calculator when I type it in. So plugging that in, if we go sine of 121, okay, divided by that answer, which is our 200.65, what we would then need to do is multiply that by 15.9 to get sine alpha by itself. And so times that by 15.9, hit enter. That gives us approximately 0.067923. Now to get alpha, we obviously need to sine inverse that. So on the calculator here, again, we'll avoid rounding issues. Go ahead and sine inverse that value. And we see that that little angle alpha there is 3.8947 degrees. Okay, again, that's not our final answer. That's just the angle between our blue and black vectors. Now what we need to do is go ahead and add the 121 to that, and there is the actual bearing of our plane. So theta would be equal to 121 plus 3.89, which means the actual course of our plane will be from due north 124 point, rounded to one decimal place here, 9 degrees. So traveling at a ground speed of 200.65 miles per hour on a bearing of 124.9 degrees from due north. So go ahead, try the example problems below. There is another example of a plane problem here that we'll look at on the next video.